Now that the rest of the world is experiencing the social life of a math teacher, I decided to make another video to talk about social distancing and how it's going to be an endurance sport. Before we talk about how long we're going to be antisocial, let's quickly review the model we built last time and improve on it. As I mentioned in the last video, I am not an epidemiologist, but a math teacher. As such, the model you see here is purely hypothetical and should not be used for anything other than educational purposes. So let's recap. Last time we built the SEIR model. We had just the three compartments that you see here, the susceptible, the infective, and the recovered. And we talked about movement between the compartments. And we introduced a bunch of parameters, including beta, which was based on the contact number, as well as other things, and also gamma, which was equal to 1 over d, where d was the duration of the infectious period. And the movement between S and I and R was modeled with these three differential equations. We actually solved really just the first two, found S of t and I of t. Then to find R of t, we just subtracted both of those from 1, giving us the susceptible, infected, and recovered fractions at any particular time t after the start of the epidemic. Since we really only needed these two, as I said just a moment ago, we were able to illustrate the trajectories on a phase plane. And this is particular for the case when we only have two differential equations. And we see the slope field there, as well as some trajectories based on different initial conditions. I decided to keep everything constant and play around only with sigma, the contact number, to see the effect on the trajectories. And we saw how we could actually flatten this curve just by being a little bit antisocial, reducing the contact number. Today, what we're going to do is, as well as building on the model, we're also going to change sigma, not at the beginning of the epidemic as we did last time, but during the epidemic, which reflects on what actually happened. And then what we're going to do is remove the restrictions, remove the social distancing measures at various times later to see how the trajectory of the epidemic is impacted. Let's get started. Now let's expand to the MSEIR model. This is going to account for births. So these people are born. They either come into the passively immune or susceptible. Deaths, which could actually happen at any stage here, but we'll talk about deaths from the infected only. And movement between all of these compartments that you see. We're only going to talk about movement from left to right. Now, in the model I build, I'm going to actually ignore births and also natural deaths. I will take into account deaths from the disease. I'm also going to pretty much ignore this completely. So really, I'm setting up the M for another time, but we're only going to be looking at the susceptible, the exposed, the infective, and the recovered. So it's really an SEIR model. And the E, the exposed compartment, this one here, is really important for the case of COVID-19 because not everyone who's exposed to this is going to become infected. And it will also build in the long latency period into the model. Before we have the differential equations, we have a bunch of constants. We have the birth rate and death rate, which we're going to ignore, as we said. So I'll set those to 0. And the mean passively immune period, that's going to also not really make much of a difference in our model. The mean latent period will, we need that. The infectious period, as before, we need that. And then in order to find beta, we have the sigma and tau as last time. So these are going to be the adequate contacts. So it's really, like I said before, an SEIR model. And from these parameters, we can calculate the net rate of population change, again, for later models, the contact rate, as we learned about, also the replacement number, which is a very important number in describing the epidemic, as well as the one you've heard about probably a whole lot, which is R naught, and the final susceptible fraction, which we discussed in the last video. Taking all of these parameters and constants, let's look at the differential equations shown. dm dt, the dt, the I dt, and the R dt. You'll notice one is missing. You'll see why it's missing in just a second. When we solve this system, we're going to end up with fractions, m of t, e of t, I of t, and R of t. Like I said before, the m doesn't really matter, but I'll just include it for completion. Now the question is, where is ds dt, the susceptibles? Now, as before, once we solve these four, we can actually just find s of t, so we don't even need ds dt. We find s by subtracting each of those, m, e, I, and R, which, oddly enough, that's my middle name. Okay, so we head over to MATLAB now to take a look at what the solutions are going to be. And you'll see that I have left off the phase plane. And the reason for that is you can only represent the solutions to a system of differential equations in a phase plane when you have two equations. Here we have four, so it's not going to be possible. Instead, we head right to the integral curves, as you see here. And you'll notice that I've taken the initial conditions, I've put them in. They're not particularly important because, like I said, this is just a hypothetical, just to give a sense of what this looks like. I've also included the mortalities. This is the deceased based on the numbers coming out of Korea, South Korea, which has a pretty high number of tests, so their mortality rate is probably closer to the true mortality rate for countries that have fewer tests. So we see the model here, and you can barely see the deceased. They're over at the bottom. We'll zoom in just a moment to see what that looks like. So as many of my students can attest, I am not a huge fan of Google Sheets. I prefer Excel. It's more user-friendly, a bit more powerful, but for the purpose of sharing, I've created this Google Sheet, and what it does is it references data coming from the exact same source that Johns Hopkins is using, and here it is. I'll link to it also in the description of the video. And I update it daily. In fact, I just updated a few minutes ago. And what it allows us to do is select a particular country or state if you're talking about the United States. So let's look at Italy for a moment. And the reason I'm doing this is not to scare people, but to then tie it back to the model that you saw just a moment ago. And this is the data from Italy, and what it shows is the confirmed cases, cumulative infected cases, and the deaths due to the virus. And the reason that I'm showing this to you is so that way we start to get a sense of where we are on the curve, because that's going to prove to be really important. So just to have a bit of perspective, let's take a look at South Korea. And you see from South Korea that even though the cumulative infected, which for Korea is probably a bit more accurate than other countries, is not perfect as a statistic, it still gives us representation of the fact that they are much further along in the epidemic than we are. Take a look now where it all started, over here in China, Hubei. And this accounts for the release of a lot of data regarding the infected, the cumulative infected, the cases. But still we can see that there is this roughly logistic curve and that they are well beyond their peak. In fact, actually, as of just yesterday, or today, they released that there were no new cases for the first time, which is a huge milestone. Back to Italy for a moment, because that's where I live, and we'll use it as an example. What I've also pulled in is a little bit of data regarding what measures were taken and when. So I start the epidemic locally, right here, with the first case that's confirmed. In fact, with Italy, it was 2. They didn't have patient 0, but patient 1. And I put in some measures that were taken, and it wasn't until day 41 that Italy as an entire country was declared a red zone. So we'll get a sense of what that means in a bit, even though at day 24 they started to close things down. Just so you have a sense of how many days it took and where we were in the curve at that point. This is 24, and you could see why people didn't always agree with the closures, whereas it might be obvious now why those were put into place as early as they were. And the reason I bring this up is because we wanted to know when it is safe to remove these measures. And of course, don't trust me, trust the authorities, but at least we'll have a sense of where we are on the curve. So we're moving back over to MATLAB, and what I've done is I've regraphed the same model from before. Now, this doesn't incorporate any social distancing measures at all. So this is just assuming that we had not taken any of those measures, which we actually have. I'll show you those models in just a moment. But what I've done is I've taken the deceased curve here, the people who have died as a result of the disease, because you can barely see it. It's at the bottom due to the scale, because this represents as a fraction of the total population, so it should be small. And by removing the other 4 curves, we allow the axis to expand, and we can actually see that it too has a bit of a logistic looking curve. And the reason that I'm showing this to you is so that way if we highlight the bottom little section of it, the first little section of it, I'll go up to about the same number of days that we're at here in Italy, and go ahead and just put our actual data, so I'm pulling the data from the exact same source here, we do get a picture of roughly where we are on the curve. Now keep in mind, of course, that this curve has gotten flatter. There'll be a bit of a time lag for every bit of the measures that are put in, but it's probably going to be a little later than we expected. So experts here are saying at least another week or so before we peak and then descend. Once we start to descend, the question remains, when is it safe to remove the social distancing measures? And we'll take a look at some of those different possibilities now. So we're going to take a look at 4 different situations. The first in the top left is just the infected curve from the model from before, but it's actually not realistic anymore because social distancing measures have been implemented. And this very roughly is used to represent the situation here in Italy. You'll see that I've removed the X-ticks, and the reason I've done so is so that way nobody uses this model as anything but something hypothetical. This should not be taken as an authority. I don't want you to go to your boss and say, well, I found some YouTube video that says we're not supposed to go back to work for this many days, but rather just to demonstrate the effect of removing social distancing at different places along the curve. And the first one over here has no social distancing measures implemented, as I said before. In the second, what I've done is roughly the same number of days, actually exactly the same number of days as Italy. We started day 41, and we see that we flatten the curve. So in all the 3 that remain, the green represents our flatter curve, roughly. Then what I have done in the first scenario over here is before even reaching the peak, let's just say not that far from now, removing, and to take it as an extreme, putting back social life as it was before, completely removing social distancing, we see we immediately get another peak in our epidemic. And what I've done, at least in the programming side of it, is I've started our system of differential equations using as initial values the ending values of this green curve here. So I've taken them and fed them back into another SEIR model to generate this curve that you see. Again, it's extreme because what we would have realistically probably slowly releasing these measures, as China's beginning to do. Then over here, we see what happens if we do it when we're actually right at the top. We see we do get another bump, so it's probably a bit early. Whereas in this final scenario, what we have is a much better situation. Now, in each scenario, the removal of the social distancing measures and returning exactly to pre-level social contact numbers is extreme, and it's to illustrate a point that these endpoints that I've chosen here, here, and here can actually become initial conditions for a second wave of the epidemic, and we don't want that. So the point is, where we are on the curve is very important because we don't want another peak. I, for one, plan to listen to the health authority recommendations on this now that I understand at the very least that where we are on the curve matters a whole lot. Once again, I'd like to say thank you to my friend Michael for all of his help in sending me tons of stuff to read and also in taking a look at the video you see here before sharing it with you fine folks.